Fancy Meat Computers! Hello, everyone! I know we didn't hit 1,000 subs, but I thought, you know, since it's the last week, we could, we could have a baby on the stream. Say hello to Mr. Felix. Felix, say hello to all of the people out there in television land, hey? Yeah. Ha! There we go. Boing! I guess this is primarily for the people who are going to be watching this thing afterwards, because I don't see anybody in the stream or anybody at all. Wow, that's kind of disappointing. Am I in the right place? Yeah, I'm in the right place. Maybe it's you guys who are in the wrong place. Wow, what? Oh, Mark is here. Okay. Well, I don't know. You were the only person here, so. Hop, baby. Boom. Boing. There we go. All right. Oh. And. There we go. And a cat. Mark said he preferred cats, so there's the cat. Say hello to everybody out there in television land, Mr. Martin. Yeah. There's a note. What? Avenue. Did I not post the... Oh, that's a shame. Did I not post the links? I didn't post the links. Shoot. God damn it. every time. All right. Boy, it's try to set things up to do something nice. Yeah. I thought that people just weren't showing up. Because, you know. That's also a thing. Because they're still stuck on P3. Yeah. And that's due today, too. I should probably answer some Piazza questions, eh? Oh, no, that's due tomorrow. Today's Tuesday. Pardon me. Today is Tuesday. So there's tomorrow and then today as well. Yeah. No more extensions this time. Yep, that's true. It's due the last day of classes, so there's no more time left to extend it to. It's sort of, you know, I was going to make it due Sunday, and then it was like, I knew lots of people would just, you know, people would just kind of wheedle extension after extension out of me anyway, so it's, you know, fine, we'll start off with maximum extension, and that's how it worked. I'm sorry, John, I gave you a fright. For those of you who just joined us, for those of you who are just joining us, I recommend taking a look at, what's the timestamp? Timestamp. Starting at 8 minutes in, I recommend taking a look. Well, yeah, like 8, sorry, closer to 9 minutes. There we go. Yeah. Take a look at 9 minutes into this video, if you're just joining us. But, anyway, so, I guess, we might as well get started. I suppose it's useless to say, are there any questions? Actually, let me see just for a moment how big the backlog on Piazza is. It's not too bad. It's not too bad. Yeah. That's got to get dealt with today. So anyway, I guess we might as well just continue on with our lectures then. Important note before we get into it. Tomorrow is a review session. So anybody who wishes to have some aspect of the course reviewed, sort of in anticipation of the final examination, this is your chance to have your professor answer your questions on a Q&A style sort of thing. So, yep. Let's get to it. So, so we were talking about advanced topics in type theory. We've talked about, in general, so far, we talked about subtyping. We've been working our way through recursive types, which are kind of fun. Well, depending on whether you think recursion is fun. But we developed this idea that if you take a list of natural numbers, it's a naturally inductive structure. So in theory, the typing should be naturally inductive as well. That way, we can represent hypothetically infinite data structures using finite representation, which of course enables us to do all kinds of interesting things, as we're going to see in a little bit. So we did this by introducing a recursion operator, mu. I know that mu is also used as the typing, or not the typing, as the data storage for, reference, when we were talking about references. So this is a different mu. This mu is the recursion operator. So essentially what we're trying to do is isolate on the right-hand side everything we need to know about this equation to know that it is recursive. So we want to eliminate the necessity of using the name of the variable in the thing again, right? So that's what the recursion operator does. And so, using that, we can say that a list is either nil or a list construction between some nat and another list. Another one of these. So, there you go. If we pull in some typing abstractions from polymorphism, which is a topic that we're going to be talking about, hopefully we'll get to it today, then you can say, so in polymorphism we provide lambda abstractions over types as well as over terms. So if you want a list in the general sense, you can also abstract out the nat, and then you have a list from, a recursively defined list where every element is of the type that is given to this type expression. So there you go. Another application of mu is the so-called hungry function. This function can accept any number of numbers and still be hungry for more. So hungry is mu a, and the typing is nat yields a, right? So it's like nat yields nat yields nat yields nat yields nat, etc., 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 etc. So in contrast to the list type, which has an option for terminating, the hungry function does not have an option for terminating. Hence, it's always hungry for more. So, this function can accept, yes, elements of this type need to be defined using the fixed point combinator or similar. So if you wanted to instantiate something with this type, you would need something recursive, like the fixed point combinator. Let's revisit omega in light of this new information. A couple of weeks ago, we concluded that the omega function was not well typed under simple type theory because we would need an arrow type for x whose domain was x itself, right? Which doesn't exist. If x has type t, the type annotation lambda x would have to be of type t yields t. Now, with recursive types, we can finally type that function. So, because we now have access to recursive types, the omega function is now well typed, which is kind of crazy. Because we were like, oh, it's not well typed, it's not well typed. Now it's well typed. Because x can actually be the infinite type mu a yields a, or a yields t, right? So if we drop that in as the typing of x, then omega suddenly becomes well typed, which is kind of amazing. This result generalizes to the fixed point combinator. So the fixed point combinator itself can be well typed in a type system that includes recursive types. So in exchange for being able to type general recursion in lambda calculus, we lose the strong normalization property, right? So in exchange for this, we lose the idea that our type system has to, like, terminate, right? The halting problem becomes undecidable again. Under simple, if you remember our topic on normalization, the simply typed lambda calculus is strongly normalizing, so it, you know, any expression will eventually terminate so long as it's well typed. Now, since we're including things that don't terminate, divergent functions can now be well typed. That means that the calculus itself loses that property, but we get some pretty cool side effects. Like, we're not just throwing away properties to gain nothing, right? So it is, in fact, possible to embed the entirety of pure lambda calculus in a recursive type system. This produces a language which is safe with respect to the well-typedness of arguments applied to functions, and which is Turing complete. So while we lose the decidability of the halting problem, right, what we gain is, number one, the ability to perform any Turing complete calculation, and B, we gain the ability, like, we maintain the ability to decide some terms are still wrongly typed, right? So we maintain the ability to say that if a function expects a nat and you give it a bool, then it's not well typed. We maintain that, and yet now we have a Turing complete system, right? So that's a pretty good gain. Although it depends on how attached you are to the halting property, I suppose. Any questions about recursive types? Well, I've got one person with me. Three people. Four. Five. And that's the majority of the class, so I'm assuming that's cool. So let's move right along, shall we? Let's talk about type reconstruction. Oh, what is the Hungry function used for? It can model file streams, or streams in general. Obviously, standard input and output, right? Hungry can be used to model those. But it's a good example of this is something that hypothetically eventually terminates, but it's also possible to construct things that are well-typed that don't. And that's, Hungry is it's like your minimal typing example of an infinitely running function. Kind of like how omega is your minimal example of a divergent function. So, in our study of simple types, we relied on type annotations to provide enough information to type our programs. In practice, type annotations can have a huge impact on the ease of use of a programming language. Some of the factors affecting language popularity are ease of use and expressive power. So, generally speaking, if a language is easier to use, it will see a greater degree of adoption. And depending on how heavy the type annotation is in that language, basically, the more Avenue is having an outage. What? Really? Well, it's no wonder people can't find a lecture. Okay, I'm going to post to Teams then. Second last day of class and Avenue's having an outage? Hilarious. Wonderful. There we go. Cool. So, the typical example of this is Python, right? Python is not the most powerful language. It is not the most rigorous language. There's really not a whole lot to recommend it, aside from the fact that it has a very expansive set of libraries, right? It's like Python is used primarily because it has super simplified syntax and because it has a great deal of good library support. Those are the two reasons. It's easy to learn, right? Because the syntax is simple. And that's one of the factors that they've drummed out of the syntax for Python is type annotations, right? You can have type what do they call them? Type hints, which don't actually, they don't actually constrain the program in any meaningful way. They're primarily there for documentation, but and everybody knows I hate Python, but yeah, Python is a very popular language because of its ease of use, and the lack of type annotations is part of its ease of use. And so what we want, we want to have ease of use, but we also don't want, we don't want our programs to not be well typed. In my opinion, Python takes it too far. If some typing information can be reconstructed or inferred from the terms of the language directly, this reduces the need for type annotations. You can program faster because you don't have to keep repeating yourself. In general, the fewer annotations a language requires, the easier it is to use. This philosophy is exemplified, and taken too far in your professor's opinion, by Python, which does not require any type annotation whatsoever. And also, Haskell uses a great deal of type inference, and of course, unlike Python, Haskell doesn't compromise the safety of its abstractions. Interesting note about Python. You know the first line of every Python function that you write that provides the typing information for the function? You don't actually need to include it. It's not a syntactic requirement. Like if you go into your project 3 that you've been working on and you delete all of the typing annotations from the first line of every Haskell function, the thing will still compile and still work. That's primarily for you. It helps out with the compiler, right? Like, those typing annotations can be used to provide more meaningful errors, type errors particularly, but they're not actually syntactically required. Haskell can get there through type inference, and the fact that it does its typing well, type polymorphism. So, recall our set of atomic types from topic 9. We left these as a set of uninterpreted base types A. At the time, we included this primarily so that we had an easy addition to pure lambda calculus, which added no evaluation semantics and removed the degeneracy of the type system. In fact, we didn't end up using atomic types very much at all. In contrast to interpreted types, such as nat and bool, it was just a placeholder for some particular types whose exact identities we didn't care about. So it didn't really matter if, if A was floats, or if A was reals, or if they were strings, didn't matter. The key question of type inference is, if I substitute the placeholder type X with some concrete type, such as bool, does the term T become well typed? This is the central question. So, in order to create type substitution, we need two components, right? So in order to be able to substitute a type for another type, we need to have a concept of what substitution means for types. And it turns out it's very similar to what you would imagine for terms. It's actually very, very similar to terms. So we need two things for a substitution, though. We need a mapping, sigma, from type variables to types, called a type substitution, and we need a means of applying this mapping to terms, i.e. we need a substitution semantic. So, for example, if we had a sigma, x becomes bool, then the type x yields x, if we applied the sigma, becomes bool yields bool. We can perform multiple substitutions simultaneously. So this is kind of an interesting point. Typing substitutions are considered to occur all at once, right? If it's a substitution like this with a comma, that's an all-at-once substitution. So x yields y would become bool yields x, because y is substituted for x yields x, and x is substituted for bool, but, notice that this stops short of these x's also being substituted for booleans, right? That's because it's all at once. The alternative to this is using function composition, right? So you can control an order in which these substitutions are applied using function composition. So if you apply y yields x yields, or y maps to x yields x first, you get x yields x yields x, and then you're changing all of the x's to bools, and then you get bool yields bool, which is more correct. Like, that's the sort of full substitution. So the rule here, then, for your brains is that substitutions using comma do not necessarily remove all instances of a freely occurring type variable. So, the semantics for type substitution should seem shockingly familiar. So, if we are performing a substitution over x, if x is the thing being substituted, then obviously we substitute it. And if not, then we just leave it alone, right? Substitution over concrete types, it does not affect them. And substitution on an arrow type is a two substitutions, so to speak. T1 gets substituted and T2 gets substituted. This should look very, 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 very similar to how substitution works in the lambda calculus over terms. The only difference of consequence between type and term substitution is that we don't yet have to worry about type variable capture. We do not yet have a way to bind type variables, but we will once we hit parametric polymorphism. So let's consider the central question, now that we know what substitution means. Let's suppose we have a term t containing type variables inside of a context gamma, which might also contain type variables, right? So essentially, we have a t and we have a gamma. There are two very different questions we could ask here, which have a radically different effect on our language design. Question number 1. Are all substitution instances well-typed? Question number 2. Are any substitution instances well-typed? So, that is to say, for all substitutions, does there exist some type such that if you perform those substitutions over gamma and the term t, that yields the type t? In the case of any substitution, that's, does there exist a substitution such that there will exist a type t, such that if you apply the substitutions to gamma and to term t, you get the type t? The answer to the first question is parametric polymorphism. Parametric polymorphism is this, you arrive at the answer to this question via parametric polymorphism. Sorry, that's not quite phrased correctly. And you arrive at the answer to this question using type inference. So, according to the first view, type variables should be held abstract during type checking. This ensures a well-typed term will behave properly no matter what concrete types are later substituted. Needless to say, this is a very high standard of correctness. Take, for example, the following term. Lambda f with type x yields x, lambda a with type x, and we apply f twice, or we apply f to a, and then we apply the result of that to f again. So it's like a function composition. You apply f twice. Whatever concrete type we replace x with, this will be well typed. However, if we have the following, so if the f gets y instead of x yields x, then this is not necessarily true. Like, this is not necessarily well typed, right? If we replace y, for example, with some concrete term like bool, this term is not well typed. So under for all x, under parametric polymorphism, this would not pass the test, right? In the second view, we are interested in whether a term can become well-typed if the substitutions are selected appropriately. So, considering that same example, let's consider considering the same example, if we have f having some type y and a having some type x, we can certainly instantiate these two type variables in such a way that this is well typed. For example, x is instantiated with nat, and y is instantiated with nat yields nat. So, like, that would make it well typed, obviously. Y yielding x would also be well typed. Of course, that's kind of just reinstantiating the answer we had to this problem earlier. But that's also a valid substitution. So this guy makes the term well typed while still containing type variables. This is, in fact, the most general substitution we can make in that we are making the least possible commitment. When I was doing out these slides, I made a mental note to myself that I should make a joke about how this should appeal to Zoomers because Zoomers hate commitment. But that's also, I think, true of millennials, so, yeah. So, looking for valid instantiations of type variables leads us to the idea of type inference. The compiler helps the programmer fill in typing annotations that may be optional. Most languages have some degree of type inference. Even in Haskell, which is strongly statically typed, relies on a heavy degree of type inferencing. That thing I said earlier is actually in the slides up here. Technically speaking, the usual first line of a Haskell function containing the function's typing information is optional. It is conventionally added for readability, however. Taken to its extreme, a language may require no type annotations from the programmer and rely on reconstruction for everything. Both Python and ML follow this approach. So here's an example. If we let gamma be a context and t a term, a solution for gamma comma t is a pair sigma comma type t such that sigma applied to gamma types sigma applied to t as the type t. So if we consider the following, a gamma is f having type x and a having type y, and then the type is f with a being applied. The following are solutions for gamma comma t. We can replace x for y, yields nat, and type it as nat. We can replace x for y, yields z, and type it as z. We could replace x with y yields z and z with nat, and then still replace with z, etc., etc., etc. These are all solutions. Any questions? I'm zooming through these slides faster than I thought I was going to, because nobody's asking any questions. It's your fault. If I run out of slides, it's your fault. You just let me talk. You just let me keep talking. That's how it works. I wonder if Avenue is no longer having an outage. This is not scheduled maintenance. Gee, I hope they fix this problem before everybody has to submit their Project 3. The baby is still getting over the cold. No! Don't just email me the submissions. That's the worst possible option. Thank you, Mark. Jeez. Ugh. Oh my god, can you imagine? That actually would be a reason I would give an extension. Is if they don't have this fixed by tomorrow, I would extend the deadline as long as, you know, Avenue was down, as long as it was only a day or two. Good lord. Okay, so, I think I might have been... Yeah, okay. We'll just stop one short of slide. Oof. Alright, so. Polymorphism, then. Let's consider the following small program. We've got double, which is not a keyword even though it's highlighted blue. It's just a name. We'll let double equal essentially that same function we had before, but the well-typed version, right? We'll let A be a double as well, or we'll let A be double with the following function and 1 applied, so that's just like add 2. And then we'd also have B having a double, having a doubling of just like basically a Boolean identity function, which is kind of dumb, but, you know, it's an example. Our current notion of type inference can't handle this example. No single substitution can type this program. X would have to be nat and bool simultaneously. However, we can achieve this with a weak form of polymorphism known as let polymorphism. The process is easy to achieve, but requires contamination of the type system with evaluation semantics. So, recall the typing rule for let bindings, right? So, a let binding is typed as whatever the type of the second term is if X has type T1 in T2, and assuming that T also has type T1. So you need type consistency between X and T1, and the the type of X is being derived from the typing of T1, and then T2 must be typed. Man, yeah. T2 must have that have type T2. So, the type of T2 is calculated by first calculating the type of T1, and then including that in gamma. I.e., the type calculation is being made up front for all occurrences of X. If we defer this type calculation until after the let binding is evaluated, and the substitution is performed, we multiply the number of type calculations we have to perform, but each one can be typed independently. So, rather than configure things this way, we could say that we require T2, the term T2, to have the type T2 if, post-substitution. So, good. Each significant piece of functionality in a program should be implemented in just one place, and in the source code. Sorry. Yes, and in the source code. Good lord, it's been a long semester. Each significant piece of functionality in a program should be implemented in just one place in the source code. Where similar functions are carried out by distinct pieces of code, it is generally beneficial to combine them, abstracting out the various parts. This is the abstraction principle of software engineering. And the way that you get to parametric polymorphism is by applying this principle to type systems. So, in general, there are three types of polymorphism, aside from let polymorphism, which is a very weak form. There are three types of polymorphism that normally occur in programming languages. This is an incomplete categorization, but it is, the major categories. So you've got parametric polymorphism, you've got ad hoc polymorphism, and you've got subtype polymorphism. So we already talked about subtype polymorphism, so we'll, leave that aside. But, yeah, those are the three types. Which type of polymorphism is being talked about is going to depend on who you're talking to, right? Polymorphism means different things to different types of programmers. Functional programmers almost always mean parametric polymorphism. Object-oriented programmers will normally mean subtype polymorphism. For them, ad hoc polymorphism will be termed overloading, and parametric polymorphism will be called genericity, something like that, or generics. Probably generics because genericity is a difficult word to pronounce. There you go. Under ad hoc polymorphism, values exhibit different behaviors when viewed with different types. The most common example of this is overloading, where a single function symbol may be associated with many implementations. I assume all of you have encountered overloading. The correct implementation is selected by the types of the arguments to the function. The addition operator in most languages is polymorphic in this way because if you add an int with an int, you get an int, and if you add a float with a float, you get a float. This selection can be made statically or dynamically. And, of course, parametric polymorphism. Parametric polymorphism works by using type variables in place of types and instantiating them as needed. Parametric definitions are uniform in that they all behave the same way. And that's all I got. Drat, I was sure that if I had prepared 20 slides, I wouldn't get through them all. This is your fault, chat. You didn't ask any questions. So I guess class is over 5 minutes early then. If you have any questions, please ask them now if you were saving them till the end. If not, I don't know. If not, if there are no questions, then I'm quitting. I am quitting this whole being a professor business, and I'm gonna be a full-time Burger Time streamer. It's like Pac-Man, but better. Yep, that's right. I'm giving the academic life a miss. It's gonna be full-time Burger Time streaming from now on. Ah. I hate it when it's like one thing left in the level and you lose. It's terrible. Doesn't even play Axiashi. Yeah. I don't have it installed on this one, to be honest. I could play my pinball game, I guess. I guess I'm supposed to be providing commentary if I'm playing a video game, eh? So... Ah, shoot. I mean, I think the game is pretty self-explanatory. I think you probably get the rules by now. I am old enough that, when I was a kid, you would go to the video rental store and pick out a game to rent for the weekend. And I'm old enough that some of those games were NES games. And this is one of the games that I used to rent when I was a young child from the video store. And when I was a child, I couldn't beat level 2. And now I can beat the whole damn thing, and I know there's only 7 levels in it. Yeah. Can't talk and play at the same time. I could try. I don't know, I'm pretty good at talking. So here's a hot burger time trick. If you catch one of the enemies on one of the hamburger buns, it'll do 3 levels down instead of just the one that you usually get. This is actually a really easy level. It's like just back and forth. Anyway. So, only 2 people still watching. So, see you tomorrow for the review session, everyone.
Thank you.